Hey, VSauce! Noah here. Look what I found. My favorite snack, a bowl of soup. Score, am I right? Oh my gosh. Let me dig in. That's really hot. Oh my gosh, that's really warm. I think I might have burned my tongue. I need the rest of VSauce. Kyle, Joey, Andrew, I need...
Hey, VSauce! Andrew here. I was just cooking myself a grilled cheese here in my kitchen. And not everyone can stand the pressures of cooking a perfect meal like mine, but you know what they say. If you can't stand the heat, get out of the kitchen. But what is heat? Heat is defined as the transfer of thermal energy from areas of high concentration to areas of lower concentration. Check out our previous video on energy to figure out exactly what that means. Heat is transferred until both systems involved have equivalent temperatures or average kinetic energy of molecules. Now, heat can be calculated using this equation, where m is the mass of the object, c sub p is the specific heat constant, and delta T is the change in temperature. Now that we know what heat is, how is it actually transferred? I mean, all I did was put my pan on the stove and somehow my grilled cheese was cooked. Well, pans are good for more than just flipping sandwiches, which, by the way, I've gotten pretty good at. They also demonstrate one mode of heat transfer: conduction. Conduction is the transfer of heat by direct contact. We can calculate the rate of transfer using this equation, where Q over T is the rate of transfer, K is the thermal conductivity of the material, A is the area of the surface, D is the thickness of the material, and delta T is the change in temperature. Come here, check this out. So in our case here, the burner is in contact with the pan, and the pan is in contact with the sandwich, right? So heat, through conduction, transfers by contact into the pan, which then transfers to the surface of the bread. Now, as this happens, the surface of the bread becomes hotter than the interior of the sandwich. So the heat travels to the interior of the sandwich, or the cheese, because it's moving to an area of lower concentration. As this happens, the cheese gets to a high enough temperature that it melts, and I get a delicious meal. I just saw this funny meme. Let me send it to my friend Jody.
I don't need.
Bruh, what is that?
Put boiled water in there and then put it in the freezer. It's never gonna freeze because it's
Boiled.
It's boiled.
It's boiled. It's boiled.
Hey, what is?
Hey, VSauce, Joey here. Thanks to my friend Andrew who sent this cool video. They talk about how boiling water works, and that got me interested. Is it true that boiling water can't freeze? That can't be true, right? Well, let's see. Right, so here we have a pot, but not just any pot, a pot full of water. Right now it's near room temperature, but I'll let it boil for a minute. What'll happen is that it'll undergo a process called vaporization, where the liquid water will become steam due to the heat being transferred from the fire to the bottom of the pot to the water. That's cool and all, but how does this all add up mathematically? Well, let's see. If we're going to solve this problem, we need the previous equation Andrew just talked about. So it'll be Q, which is heat measured in joules, equals M mass measured in grams times C of P, which is a specific heat measured in joules per grams, times delta T, which is change in temperature, which is either measured in Kelvin or Celsius. It doesn't matter. What's being drawn here is a phase change graph. You can see where the solid and liquid are. It takes a specific amount of energy to reach from solid to liquid or liquid to gas, or gas to liquid, or liquid to solid. From liquid to gas would be called vaporization, which is what we will be doing with boiling. if you want to go down the chart, you must lose energy, and if you want to go up the chart, you must gain energy. We're going to do an example problem. We're going to use the equation Q equals mc delta T that our friend Andrew gave us. And we're also going to use the equation joules equals mass times latent heat. We'll start with initial temperature being 20 Celsius. And then the mass will be 473 grams. And the specific heat of water will be 4.106 joules per gram. And then the latent heat of water will be 2,230 joules per gram. And then we're going to put these equations together to find how many joules it takes for the water to boil. So with 473 grams multiplied by the specific heat of water times the change in temperature, we're going to be going from 20 Celsius to 100 Celsius, because that's what temperature it must be to boil, and that'll be a 80 Celsius difference. Then we're going to add the other equation, which will be 473 grams for the mass and 2,230 joules per gram for the latent heat. And if we add all this up in the handy dandy calculator, we're going to figure out that the total energy used to boil this much water would be 1,213,188.24 joules.
Phew, is it hot in here? Or did we just use a lot of brain power? We could also use this equation to calculate the energy change when we freeze our water, but we don't have to do that right now. Let's freeze our boiled water and see if it passes the test. Now, according to the awesome dude in the video, this water should not freeze at all. So let's see how this turns out. I'm excited for the results, so I'll just be waiting here for a bit. Okay, let's see what we got here. Okay, now what the heck? Why are they frozen? Did I do something wrong? Well, actually, no. Let's take a look. Well, now we have these forbidden ice cubes, but no drink to put them in. Let's see if our good friend Noah can make some use out of them.
Thanks, Joey. That ice cube took a ton of heat energy off my tongue. But how did my bowl of soup get so hot in the first place? Well, if we've already done conduction and convection, that must leave me with radiation. Now, that does not sound good, but what is radiation? While radiation may make you think of terrible toxic rays, there's radiation all around us all the time. Really, radiation is just heat transfer through electromagnetic waves. So, no medium is needed to be able to transfer the heat. But how does this work? If there's no medium, how does the energy transfer? While I'm experiencing some convection and conduction from the bowl, I'm also experiencing some radiation through infrared light. This infrared light is being emitted because as we added heat with the microwave, the heat of the bowl really grew, so it needed some place to emit a lot of its radiation, and it does that through infrared light. If we were to look at it with an infrared camera, we'd be able to see that it's very, very bright and has a lot of rays coming off of it, and that is how it radiates. The rate of heat transfer by radiation is calculated with this equation. P, the rate of transfer, equals epsilon sigma A t to the fourth. Now P is equal to the rate of transfer, and that is the change in heat over the change in time. That's equal to emissivity, which is really just an object's ability to absorb and emit radiation. So the higher it is between 0 and 1, the closer to 1 it is, the easier it is to absorb and to emit radiation. It's very efficient with radiation. And the lower it is, closer to 0, the harder it will be to emit and the harder it will be to absorb radiation. The Stefan-Boltzmann constant is the constant used for this equation, which is called the Stefan-Boltzmann equation. And the area is the surface area of whatever substance you're considering. And the temperature is the temperature of your object at any point in time. So what the flow rate is calculating at that point in time with that temperature, with the surface area of the object that you've chosen. So emissivity, you're going to have to find, sort of like a specific heat, what object you're considering, and that will be a constant no matter what equation. So if it's water, it's going to be around 0.9, and if it's some like aluminum, it'll be down by about 0.1. So you find all those, and that will give you the flow rate of your object via radiation.
Microwaves, waves, electromagnetic waves, electromagnetic spectrum. All the waves that transfer through food are electromagnetic waves of about 2.45 gigahertz, and that means that they literally are microwaves coming from your microwave oven. These waves come from a device called a magnetron, and a magnetron has a wire with a tube around it, and as the wire has current shot through it, an electric field is created circular around that wire, which then consequently creates a magnetic field perpendicular. So when electrons are shot out of that wire, the electrons are launched with the magnetic field through your microwave from a little hole in the wall, or a very thin piece of material, and it'll come through at 2.45 million times per second, and that's what creates your microwave, and that's what hits your food.
As the electromagnetic wave shoots through your food, it takes advantage of polarized particles that are in there. Mainly water, because water is in almost anything and is very easy to spin at a very high speed. So water has a positive end and a negative end, and as the electromagnetic wave comes through, it's able to attract the water and the different ends of it and constantly create it to spin faster and faster. And the 2.45 gigahertz is ideal for making the water spin at basically its highest speed. And so that makes all of the molecules within the substance heat up, gain a ton of energy and movement, and that is what creates the heat in a microwave.
It's boiled. It's boiled. Hey VSauce, Joey here. Thanks to my friend Andrew, I just sent this video. They talk about how even if you
Milk.
Let's go again. Well, act natural first.
Act natural. Act natural. Right. So here we have a pot of water. How many kills? Right. So here we have a pot, but not just any pot. A pot full of water. Right now, the water in the pot is about. Why is your writing so poopy? I hate it. Just delete that.